Hi everyone, we are back, and let's go ahead and look at our Pset 3 solutions, and let's get into it. So we're looking at figure below, two materials, perfectly bonded plates. So I am perfectly bonded here and here and here, but allowed to expand freely in this 3 direction. So looking at my material, so my yellow material has a Young's modulus of 1 GPa. Blue material, which should be green, so the green material is the blue material, has this Young's modulus. Yellow material has a thermal co-expansion of this. The green material has of this. Heated up from room temperature to 70 C. Write the full stress and strain temperature quantitatively. Yellow has Poisson's ratio of this. All right, so let's go ahead and open up our Mathematica notebook, and let's start to kind of write some of these values down. So I've got in my new notebook, because I want to write the stress and strain in my yellow material. So hopefully people can see this. And actually we'll zoom in a little bit just to make it clear. So my Y, Young's modulus of my metal material, is 1 times 10 to 9 GPa. My nu is equal to 0.28. My alpha Y, oops, I'm going to clear my, let's quit the kernel. My alpha Y is equal to 8 times 10 to the minus 6. My alpha green is equal to 78 times 10 to the minus 6. And what else do we have here? Oh, our temperature increase, our del T, went from basically 70 to 25, or actually 25 is my final. That's my temperature, so that's my del T. And then I could also define, oops, hopefully that's not gone. So I could also define my thermal strain. My thermal strain here is going to be defined as alpha times delta T. So I'll have some thermal strain of Y and some thermal strain of my green material as well. So my ETG is going to be alpha G times del T, and then my ETY is going to be equal to alpha Y times del T. So let's go ahead and get those values. And we should see that my ETG should expand. It should be about an order of magnitude larger. Thinking, Mathematica. So let's look at this numerically. Let's look at this numerically here. And yeah, so it's going to expand further. So let's figure out what stress and strain tensors we're going to have here. So there's no stress initially in our material, but as we heat it up, this green material is extremely thick compared to the yellow material. So the yellow material is going to expand just as much as this green material. So the green material is going to govern essentially the expansion here. So we are going to get some expansion, some strain in the 2-2. And we're also going to get some expansion as the material expands in the 1-1. Looking at my thermal expansion, it's much larger in my green material. So the yellow material doesn't want to expand, but it's going to be forced to because of this perfectly bonded structure. So this epsilon 1-1 is going to be equal to this epsilon 2-2, which is going to be equal to my ET of my green. So I'm going to go ahead and type that down right now. So E11 equals ETG, and then E22 equals E11. Fantastic. Now the material is also going to be able to expand in the 3 direction. And we don't know what the 3 direction, it's going to be a combination of different values as well. Now, where are their stresses? So I'm going to assume perfectly bonding, so there's not going to be any shear stresses in between them. There might be, but I'm going to assume that there's none, so I'm just going to have these normal stresses. So this yellow material only wants to expand this much, for example, but it's going to expand this whole other direction because of the green material's expansion. So it's essentially a force that's acting. The green material is going to basically expand and pull this material in tension. So there will be indeed a stress in the 1-1, a stress in the 2-2. What about in the 3-3? Nope, it's free to expand. So now this is an unknown, this is an unknown, and this is my unknown. I know this, and now we could go ahead and solve the problem. So I'm going to write out my 3 equations, my 3 unknowns. So we said that sig3 was equal to 0. So now let's go ahead and write out and solve our equations. So I'd have this one ready and in the chamber essentially. I'm going to write out y times sig1 minus nu times sig22 plus sig33 And now remember, this is my strain in the 1-1 direction. So it's governed by the G, but I also have to consider that thermal expansion in addition to the stresses. So plus ETY, because I'm looking at my Y material. So I'm going to control this, I'm going to copy. I'm going to solve for my SIG11, my SIG22, my E33. I need to change this to 22, this to 22, this to 11. This should be 11, this should be 33, this should be 33. And I'm going to solve. Oops, let's solve on this numerically. Oops. Let's see here. Where have I made a teensy mistake? I think I probably miswrote SIG11. 1 second here. I see. So the issue here is, and we're going to need to quit our kernel, we need to do the double equal sign. So whenever you're doing solve, double equal, and then double equal. I'm going to just run this whole thing over again, because once you've set equal, then it's going to kind of, so let's just evaluate the notebook. Let's see our values. What will be, and we see our stress, and then we also have the strain is negative, and again the strain is negative because we have this 1 order of magnitude difference between our green expansion, so it's going to pull that thing quite a bit flat. So that's number 1 done. Except for, how would your answer above change if now there's a rigid metal plate directly in contact with the top of the yellow material? So if we look at our stress tensor here, it's exactly the same. So we're still going to have stress in the 1-1, stress in the 2-2, and we may have now a stress in the 3-3, or actually if we look at our material, so stress in the stress tensor, again we still have strain in the 1-1, strain in the 2-2. Now we may have a stress if this material were to expand, but we see that it actually contracts in the 3-3 direction. So this is still 0, and then our thermal expansion, we still have a strain here, because again, it's not going to, that plate it's not going to expand, so it's not going to constrain it from expanding, but it actually contracts, so we still have the same values. So that's it for problem 1. So now let's go ahead and go to problem 2. So now on to problem 2. So our yellow material is sandwiched between 2 rigid plates again, bonded in some way. The temperature now decreases from room temperature to minus 100 C. Write the full stress and strain tensors quantitatively. So typically, I always want to kind of clear my notebook. So I'm going to quit my kernel and everything else. But we are given essentially the same material, my same alpha here. So I'm going to pull this out here. And then we are told that our del T now is equal to, let's go ahead and go over here. So if we look at our del T now, we see that the temperature decreases from room temperature to minus 100 C. So again, my final temperature is minus 100. So what is it? So our final temperature minus 100, minus 25. So our del T will be as follows. So we're going to drop that temperature. Again, doesn't matter if you're, oops. Uh-oh. No, hopefully mathematical will respond. Not our day. Anyways, let's go ahead and rewrite that. Sorry about that. But that's unfortunately how things go sometimes when you're dealing with Mathematica and working with these. So it's actually better because we don't have to worry about anything. So y is equal to 1 times 10 to the 9. My nu, let's kind of zoom in here for the audience. My nu is equal to 0.28. My alpha is equal to 8 times 10 to the minus 6. And then our basically del T equals minus 100 minus 25. And voila. So we've got that. We've got all those other values. And so now we can start to work on this problem. So we need to write the full stress and strain tensors again. So for this scenario. So let's go ahead and let's keep these right here. And let's start to write. So I'm going to erase from our previous problem set. So now our material is bonded and we're decreasing the temperature. So we decrease the temperature, so the material should want to kind of contract in all those directions. So we are bonded here at this surface. So the material is going to want to contract, but these are rigid walls that are kind of stuck here, so they're not going to move. So I am not going to have, in the 2-2 direction, there is not, or in the 2-2 direction, there's going to be 0 strain. In the 1-1 direction, I'm actually free to contract. Same thing in the 3-3 direction. 3-3. So 2-2, I cannot expand or contract. In the 1-1 I can, and the 3-3 I can. What about stresses? Well, if I can expand freely here and here, there's no stress here, but there will be a stress in the 2-2 direction because again, the material wants to contract, but it's not allowed to effectively. So, and again, I'm ignoring essentially shear because we're perfectly bonded on the wall. I'm ignoring edge effects here that really constrain the motion at these edges due to the bonding process, but those are the assumptions that I'm going to make. So, I don't know this, I don't know this, and I don't know this. But I have 3 equations, I have 3 unknowns. Let's solve them once again. So I need to do solve. I really wish now I had my mathematic the previous solution. So epsilon 1, actually let's go ahead and define. So our tensors. So I'm going to do sig11 is equal to 0, sig33 equals to 0, and then e22 equals 0. So e11 equals 1 divided by y times my sig11 minus nu times sig22 plus sig33. I have my correct equation now. I need to add that thermal strain. Be careful. Alpha times del T. So I've got this one. I want to do here, here, close it, solving for sig22, sig11. Actually, I'm going to shift enter this right now. Sig11, and then actually E11, E33. And so I've got my 2-2 here. I've got my 3-3 here. And then here we're going to change this to 2-2. This is going to become 1-1. This will also become 1-1. This becomes 3-3. And then I can solve. And I get those values. So the strain in the 1-1, again, is going to contract. Makes sense. 3-3 as well. And then the stress there, again, it's basically in tension because the material wants to contract, but it's pulling it in the opposite direction. Makes sense. Fantastic. So now let's get into problem 3. And we are back. So let's do problem 3 right now. So I have a polymer PVC that is primarily bonded through intermolecular bonds. It can be modeled via the Leonard-Jones potential. So let's go ahead and kind of start to, again, evaluate, clear my kernel. I know that I can model the ULJ is equal to, let's go ahead and let's confirm. Let's actually go into Canvas and let's look at our lecture notes. Let's find our Leonard-Jones potential. So we know we could find our lecture notes just to make sure we have our potentials all correct. I believe it should be 4 epsilon, but I want to make sure. Yep, 4 epsilon. So let's go ahead. Leonard-Jones is equal to 4 times epsilon times sigma divided by r to the 12th minus sigma divided by r to the 6th. So we'll put that there. ULJ, let's check it out and see if it looks okay. Excellent. So our epsilon equals basically a KT, where K is equal to our Boltzmann's constant, 1.38 times 10 to the minus 23. Our T is room temperature, so our epsilon equals K times 298 at room temperature. So that's our epsilon. Our sigma, let's see what we're given in our problem statement. Our sigma is equal to 5 angstroms. So sigma equals to 5 times 10 to the minus 10. So that's our sigma. So I also want to look up PVC. So I need to look at the TG of PVC. And then I also need, maximum, where is our TG? Glass transition temperature. Let's say it's around, so about 82C. So if I look at, let's go ahead and actually examine this. So if I look at PVC, let's see. So if I look at PVC, there's some different values. Let's look at actually. So yeah, PVC, I usually see around 60C. So my TG is at 60C. So from 0 to 60C, I could treat this as our kind of usual Young's modulus calculation, because that's what we're asked to do. So describe the Young's modulus from 0. So from 0, technically this only works at 0, but I can do, again, I'm going to take the derivative of ULJ with respect to R. I'm going to find my equilibrium distance. So I'm going to solve for when this set equals to 0. I want the reals. Solve for R, and I want the reals. So this is my R naught. Control C. So my R naught equals this. I'm going to use this definition for Young's modulus. So Y before TG. So from 0 to 60. So actually, really at 0, Y equals 1 divided by R naught, and then derivative of ULJ, R to the second, and then I'm going to evaluate this slash dot R goes to R naught, and that's my Young's modulus. Looks pretty good, gigapascal, pretty accurate actually, shockingly accurate, very, very good. So that is what I can do for a polymer. Now, once I get above 60, above TG, I need to use our other definition. And we have looked at that in our rubber elasticity lecture, which was in lecture 7. So we have this beautiful equation for the Young's modulus of, it's way past. This was such a beautiful lecture, if I don't say so myself. So I look at rubber elasticity and we go through all of our derivations. At the end of the day, we were given this expression. So I can rewrite it. We're given essentially nx, basically the number density. So our nx in this problem, so my nx equals, what is it? 10 to the 26. So that's my number of crosslinks per unit volume, 10 to the 26 power. So a lot of crosslinks, kind of. So that is nx, and then my Avogadro's number, Na, is equal to 6.02 times 10 to the 23rd. So I can write and actually determine, and actually I need to look at also what is the density of PVC. So PVC in kilojoules per kilogram. Meter cubed. So PVC, so it's about 1,400. So my rho equals 1,467. So that's my density. So I could kind of solve and actually look for the rest of this expression. So my m sub x, my m sub x equals, mx equals rho divided by nx divided by na, and that's my mx. So I could do, and basically write that out. You could also see that if I rewrite this Young's modulus is just, so you could kind of rewrite this. If mx is this, so let's go ahead and actually write this out. So if my mx equals, what is that? Equals rho, let me rewrite this here, equals rho over basically nx na. So I could rewrite this mx expression as well. So we usually have E is equal to, let's go ahead and go back here. E is equal to rho na over mx, equal to rho na over mx, and then I think it's a kt, but let's just double check this. Yep, a kt. So I can rewrite this expression. So if I resolve this for nx, flip this over on this side, equals rho NA over mx. So really, E is just going to be equal to nx times kt, which makes sense because this is my Young's modulus, right? So this is the number of crosslinks, so just a number over meter cubed. This is kt, which is what? It's going to be a joule. Joule is equal to a Newton per meter. So a Newton meter divided by meter cubed is going to be your cross-sectional area. So I could just do nx times k times my temperature. Basically, if I look at 60 C, so 60 plus 273 would be this, and then all the way, you can see the big drop off, right? So I went from a gigapascal to basically looking at something that's more on the order of 400, actually really like 0.4 megapascals. So 60 plus 80 would be here. So there you go. Problem 3 is done. So now let's get into problem 4, which is a doozy. I like it. See you in the next one. We're back and let's get into problem 4, which I really like. So this is a rubber elasticity problem. So we can no longer use kind of our traditional framework. We really need to use our kind of rubber elasticity equation. So we need to make sure that alpha 1, alpha 2, alpha 3 is equal to 1. And we also need to make sure that my delta S is equal to minus K over 2 times alpha 1 squared plus alpha 2 squared plus alpha 3 squared minus 3. And then my force in any direction I is going to be minus T times the derivative of delta S dLi. That's it. So we need to use this expression. We need to use this incompressibility expression as well. So I placed my rubber elastic material and there's a compressive force that these black boxes, the blacks, basically spots, these black blocks exert on here. So my rubber is red. It's a parallel, rectangular parallel pipette with a length of, so my length going into the boards in the 1 direction is 15 meters. My width here is 5 inches. And then my thickness here is going to be 18 millimeters. So I need to make sure the rubber does not stick out of the apparatus in the 1 direction more than 300 micrometers. So I'm constrained here. I also have these walls on the 2 side that constrain the material from expanding there. So I need to figure out what's the force in the 3 directions. So they're going to exert, there's some force that's exerted here that's going to compress it, and then the material is going to jut out in this direction. So there's no real force in the 1 direction. So essentially that's what's kind of happening in this problem. There is some force in the 2 direction as well, but anyways, we'll kind of get into that. That's a problem for another day. So we're really interested only in the force in the 3 direction, stress in the 3 direction, and then we're also given some values that will help us kind of calculate our Young's modulus as well in this material, and also the forces. So let's go ahead and work with this. So the key thing here is in the 2 direction, my material can't expand. So if I look at my alpha 2, it's the new length in the 2 direction over my initial length in the 2 direction. So if my material can't expand, this alpha 2 is going to be equal to 1. Once that is set, I can now write that alpha, there is going to be some change in the 3 direction. So in that thickness, because there's a force that's exerted on it. So there's going to be some change in alpha 3, and we're interested in that. What's the new 3 direction relative to the initial direction? So I don't know what this is, but I also know that I need to make sure alpha 1, alpha 2, and alpha 3 all equal 1. So if alpha 2 equals 1, then I know that alpha 3, basically, I need to make sure if this is equal to 1, my alpha 1 must be equal to 1 over alpha 3. That's it. So I have this relationship. So now I could go and start to kind of plug in here. Now, I probably shouldn't, actually will right now. I'm going to quit the kernel, and then I'm going to start to kind of plug in values again. So, but I want to keep my k, 3 times 10. So I want to put the k here, and then we're going to go ahead here, and then let's go ahead and do my del S equals basically minus k over 2, minus k over 2 times alpha 1 squared plus alpha 2 squared plus alpha 3 squared minus 3. And then we know that alpha 2 is equal to 1, and that alpha 1 equals 1 divided by alpha 3. And so we could plug that in here. So we don't know what alpha 3 is. Now I'm going to take the derivative, and I'm going to say that we'll plug in alpha 3 is equal to L3 divided by my L naught, effectively. So this value here. So the L naught, I'm going to say L naught 3, excuse me. So the initial direction there. So I could type out del S again. Got that. So I'm going to take the derivative. Again, so my F3 is going to be minus T times the derivative of del S in regards to L3, because I'm looking for the force in the 3 direction. So I have got that value. So that is my value of force. So I can now start to basically plug in and solve out for the rest of those values. So this is the force per chain. So that's a very important kind of distinction here. And I believe that we're told here, we could assume that we're at room temperature. So we know what our T is, so I could start to kind of substitute it in. So I could look at F3, my force in the 3 direction. If I look at per chain now, I can start to plug in for these values, because I can actually figure out what that length is going to be based on all those other values. But let's keep it general, and let's try to, because we're not really interested in the force per chain, we're looking at the total force. So the total force in that direction, actually the stress, essentially, it is going to be F1 times the number of these subchains. So, and the number of the subchains can be related. So we need to actually divide. So if I want to start to kind of get out the stress, so the stress in the 3 is going to be equal to, again, the number of subchains F3, and then I need to divide that by the A naught. So what is the area that that force in the 3 direction is acting on? So let's go over here. So it is acting on, the force in the 3 direction is acting on my initial length in the 2 direction, and then my initial length in the 1 direction. So I'm looking and pulling out L naught 1 times L naught 2. So that's my stress in the 3. Now you could also see I could pull out this L naught 3 here. So I could actually divide this out, or actually pull out that, and I could get essentially the volume. So if I make some changes to this expression, I could get the number of crossings per volume, because the volume is just going to be L naught 1, L naught 2, L naught 3. And we see I could pull out the L naught here and the L naught here. So if I actually divide out or pull out an L naught, I can kind of get this expression. So, or I can kind of just plug in my values here, because I actually know what those L naughts are. So there's lots of ways to kind of solve this problem. So I could basically start to substitute in, but again, the number of basically chains per unit volume is going to be, essentially the same there. So my Z is essentially the number of chains per unit volume. So actually, we could actually go and get rid of this. So if I basically look at F3, and if I divide F3 by, if I basically remove an L3, L naught 3, let's take a look at how it looks like. Let's do basically full simplify. So it would just be here. It'd be, again, we remove, yes, exactly. So you remove the L naught 3 here, you'd add one here. So if I plug this in, so I could do this now. This is my F sub 3. So that's my force in the 3 direction. And then I just need to now, basically what we've done is now we just need to multiply this. Again, we have that KT that's still, actually that's already kind of plugged in. And then now I just need to multiply by my N sub X, my number of crosslinks. And then we're also given that in this problem, which is 10 to the 28. So now I can just do 10 times 10 to the 28. So stress 3, again, equals 10 to the 28. So, and now I could start to plug in for the rest of those values. So, what is my slash dot? My T goes to 25, or actually 298. My L naught 3 goes to what? So what was my initial? It is 18 millimeters. So let's go ahead and pick that out. Equals 18 millimeters. So basically 18 times 10 to the minus 3. And then finally, my L3. I can solve for L3 in this problem. How? Well, let's look back. We know that that alpha 1 was equal to 1. So where is alpha 2? Excuse me. Alpha 2 is equal to 1, and then my alpha 1 is equal to 1 over alpha 3. So I can solve basically 1 divided by L3 divided by L03, where we'll just plug in L03 right here. So the 18 millimeters. Control C. So this is my 18 millimeters right here. And I know that my alpha 1 is the change. So remember, we said, so I need to solve. My new change in my new direction in the 1 is simply going to be 15 meters plus 300 times 10 to the minus 6, because I'm adding those, you're jutting out just a little bit there, and then divided by 15, and then set this equal here, and then solve. So let's numerically solve. So this is my L3. So my L3 is going to change this much, so I could just substitute that in. L3 goes to this. And actually, L3 actually will be exactly that. And then multiply that out. Look at this numerically. Why is not? Oh, L not 3. L not 3. And so there would be the stress. The force, we could just do stress 3 again divided by, or multiplied by the area. So again, I could just do stress 3 again equals, if I wanted to do the force, it'd just be times the area. So my initial area is basically 5, say 5 times 0.0254, and then what is it, width there, and then basically the length would be 15 meters. So yeah, it's fairly ridiculous. So if I look at the force, this, so actually quite a tremendous force. So anyways, so that's essentially your force. So this is fantastic. So if I was designing material in Antarctica versus Brawley, California, Brawley is extremely hot. That Young's modulus might be larger. So if you're kind of looking at how the material responds, that would be one concern. And your temperature might be high enough where you lose some of this affine deformation, some of our assumptions. So let's get into problem 5, which is a natural extension. All right, so let's look at number 5. So derive the equation for stress in the 1 and 2 direction for a rubber elastic material, considering a biaxial stress state and the 1-2 plane, no shear stress. So I'm looking at a coordinate system like this, 1, 2, 3. I have a material like this. There is a stress in the 1-1 direction. There is a stress in the 2-2 direction, and that's it. So if I want to derive the equation for stress in the 1 and the 2 direction, so all I'm going to do is look at the force, and then we're going to divide out by the area, and we can get that expression. So I am going to assume that there is a change in the alpha 1. So alpha 1 exists. There's also a change in the alpha 2. So if I need to make sure that alpha 1 times alpha 2 times alpha 3 equals 1, I know then that alpha 3 is equal to 1 over alpha 1 times alpha 2. So I'm going to plug in to that expression that we did previously. So I'm going to, first off, I'm going to quit my kernel. I am going to keep my K definition. I'm going to look here. Move this down, move this down. So I'm going to keep this. I'm going to define that alpha 3 equals 1 divided by alpha 1 times alpha 2. Here, alpha 3, del S. I could plug that in. So if I'm looking for the force in the 2 direction, it's going to be minus T times my derivative of del S with respect to L2. And I'm actually, let me define here, my alpha 1 equals basically as L2 divided by L naught 2. Actually, L1, excuse me. L1 divided by L naught 1. Alpha 2 equals L2 divided by L naught 2. And then del S here, here. Got this. That's my force. And then this would be for my force in the 1 direction. I don't know why I chose 2 first, but it's okay. That's there. If I want to do the stress 1, it's just going to be Z, the number of basically cross links, times F1 divided by basically my area, which is going to be L naught 2 times L naught 3. That, and then the same thing for here, except let's see the stress, the 2, F and the 2, L naught 1, L naught 3. That's it. So nasty little expression, but it works. So on to number 6. So we are traveling back in time to the age of disco. I'm pretty sure all of you do not know anything about that. So anyways, so at Studio 54, I'm going to wear platform shoes. So the platform material was made quite shoddily. So I'm looking at a material, something like this. So made quite shoddily. So often you see the height decrease from, basically we have a distance here that's 8 inches. So we go from 8 inches all the way down to 4 inches. So already looking at my coordinate system here, 1, 2, 3, I have some strain in the 3 direction. So my strain in the 3 direction, I'm going to quit my kernel again, as always. So my E33 is equal to my final, which is, again, be careful here. I know what I'm doing with the inches, so I'm going to just kind of do it quickly. Final minus initial divided by initial. So 4 inches here, here. So we get that value. So that is my, oops. Oh no, not again. Oh, Mathematica, you're letting me down. But anyways, it's okay. We don't need it too badly on this problem. Let's continue. Open up Mathematica. There we go. All right. So my strain in the 3-3 is equal to, let me zoom in again here. So my not that much. Strain in the 3-3 is equal to my finite dimensions minus 8 divided by 8. So that's my strain in the 3-3. Now, if I look here, so I have a strain in the 3-3. So if I look at my stress tensor, so I have a strain in the 3-3, and we know that value. It also says that you, from a top-down view, you see the material has expanded laterally. So if I'm looking top-down, my material has expanded in this direction, basically to a value of from 2 inches from its initial width of 12 inches. So it's expanded this additional distance. So my final, so if I'm looking at, for example, like my strain in the 2-2, it's going to be 12 minus 10 divided by 10. So that's my strain in the 2-2 direction. Now, if I'm thinking about this problem, if I have some strain in the 2-2. Now I'm not sure exactly what the strain in the 1-1 is going to be because I don't know what the material, I don't know what's the shape of the shoe. I'm only kind of told that kind of width essentially. I don't know what the length is necessarily. So I need to kind of figure out, well, I can kind of relate this here. So I have my Poisson's ratio is minus the lateral expansion. So essentially my strain in the 2-2 over the axial, basically compression as well. Strain in the 3-3. So if I do that, so my nu equals minus my lateral, usually it's the lateral contraction, but here it's compression. So my nu is equal to 0.4. So with that, I can start to figure out, well, if it's 0.4, I kind of know what the polymer is going to be as well. So if let's start to kind of look at this. So I have a strain in the 1-1. So I know this one, I know this one. So in terms of the stress, I know that there's a stress in the 3-3. What about elsewhere? Will there be any other stress? I mean, not really. The other materials are allowed to kind of expand. So this is an over-constrained problem. So I need to figure out what is my stress in the 3-3. I need to figure out what's my value here. So let's go ahead and let's solve it. So I can go ahead, proceed with the rest of these problems. So my E11, actually solve that my E11, set it equal to 1 divided by y. There's no temperature change here, minus, actually, times sig11. And we also know that basically here that's sig11 equals 0, sig22 equals 0, and then sig11 minus nu times sig22 plus sig33. And then you know the procedure from here on out. Boom, boom. here, and then I'm going to solve for y. I want to solve for E11, and I want to solve for sig33. Actually, we're not over-constrained. You could have made the assumption that it's a polymer. Now, we could solve this problem and try to assume that y is unknown, but since we know it's pretty reasonable, again, shoes, what they're made of, if they're new as 4 or 0.4, we think it's a polymeric material, so 1 times 10 to the 9th. So I could assume that. Now I could change and actually solve for these values, get rid of y here. So that is my sigma 11, sigma 33. Looks pretty reasonable to me. Now what were we asked to do? So we're looked and said, what are the materials rated of? Write out the full stress and strain tensors quantitatively. We've got that. What is the weight of the person wearing the shoes? So we know that if we can look at the force now. So if my force is going to be equal to my sig33, actually, so this is my stress. So stress is equal to force divided by a unit area. We're going to solve this. So where is my force being applied? So I'm pressing down, and I can't really assume that I know the strain, but I actually can't solve the rest of this problem because I don't know what's that cross-sectional area that's being acted on. I know the strain, but it could be a varying dimension. So we can't actually solve the rest of this problem, but that's how you would set it up. You measure the force, figure out the weight, but that's it. Excellent. So now let's get on to question number 7. So we did 6, we were fine. So take a look at the following material below. Gray material, mystery material behaves like a ceramic. So I already know that E is equal to 300 GPa. My nu is equal to 0.2. We'll look at that later. Interesting in playing with this blue striations that are oriented approximately, so 58 degrees. So basically we're looking at a 2-3 plane that's oriented like this. So this is my 3 prime. This would be my say my 2 prime, and that angle would be 58 degrees. When I stress the material along these striations, I obtain the following stress rate below an MPa, and then it's asking, I need the stress rate from my, what was the stress in the 2-3 plane for the original coordinate system. So I want to quit my kernel, and I also want to open up a notebook on our Canvas site that should have something like this. So, oops, doesn't like the beeps, but it doesn't matter. So let's go ahead and the problem is going to ask us to solve them in all the 3 ways that we looked at in class, but we will not be doing that. We will be doing the linear algebra approach. So let's go ahead and let's minimize this a little bit. So let's go ahead and pull this over to the side. I've got my T matrix. Let's go back to our problem. So we're given the following stress state. So I am going to call this, so this was my, basically my new stress. So that was equal to minus 37, 18, and then minus 6. And I'm going to have this all times 10 to the 6 because it's megapascals. So that was my new stress. To get to my old stress system, I'm just going to do T dot my new stress slash dot. So my old stress equals, and then my theta is going to go to, so we're going to do, we did a 58 clockwise rotation, so now we need to do 58 degrees counterclockwise to get us back into our old stress state. Let's look at this numerically. Oops. And voila, we get the following values. So that's my old stress state. So now I need to figure out what are my, what are my principal stresses. What's my principal stress state? What's the angle required? Maximum shear, the stress state, and the angle to get there. So I'm going to go ahead and solve. So I need to solve for when my basically T dot old stress. When does this become 0? So the third equation. So at what value of theta? So I'm going to do that. I want to look at this numerically. So this is my angle. So theta p principal is this. So what's my stress state there? So if I do T dot old stress slash dot theta goes to theta p, and then voila, this is 0. So that is the rotation. So I need to go take from my original coordinate system, I need to go counterclockwise 38.145 degrees in order to get there. So to find my maximum shear stresses, I could also do and basically look at T dot old stress, and then I want to look at that third equation. I think I know. So if I'm in that principal stress state, then I need to go an additional, so I need to add, basically, we could try this. So let's do T dot old stress slash dot theta goes to theta P plus 45. So we should be able to get that, but let's double check it. So if I want to maximize my shear stress, I'm going to take the derivative of this with respect to theta, and I'm going to solve for theta. So maximizing this equation, and you'll see this. Let's see if that is theta P plus 45. What do you know? Same value. So we've got it. Sorry, let's show that again. 83.145, 83.145. So again, I could kind of plug that in, and there's my value. See, center of my circle. We've got it. So I'm not going to do all three methods, but all right. So the problem above, write out the strain tensors for the stress state along the striation, coordinate system, principal stress state, maximum shear stress state. What is the shear modulus for this material? What components of the strain tensor would you change if temperature changes? So for that answer, we know that it's only going to be our normal components. So our normal strain components. So we've got that one answered. But let's go ahead and continue on this route. So I need to figure out, so I've got my value of old stress, and I need to write out my S is going to be equal to my old stress my S is going to be, and I'm going to define Y equals 300 times 10 to the 9th times 10 to the 9. My nu is equal to 0.2. So those are those values there. So this is going to be 1 divided by Y minus nu divided by Y, and then 0. And then this is going to be minus nu divided by Y, 1 divided by Y, 0, and then finally 0, 0, 1 plus nu, let me do this, oops, 1 plus nu divided by Y. So I got those, and then, so now I'm just going to do my old strain is going to be equal to S dot old stress. And those would be my strain values. So if I were now asked basically to look at, again, the strain tensor, you could do it for all three directions as well. But again, we're sticking with plane stress, so that's what the problem's essentially asking for. So I've got the strain tensor for the, basically, our old coordinate system. So for the original coordinate system, I could just do the exact same thing. So I could just do, so my new strain will be equal to T dot S dot inverse T dot old stress. So then slash dot theta goes to minus 58. I think that's, actually theta goes to, let's see, let's think about this. So I'm looking to do it in my new coordinate system, which was a 58 rotation. So actually this would be my new stress. So my new stress would be in that new coordinate system. Yep. And then we can also look at that T dot old strain slash dot theta goes to 58. And got a little bit of a different value, but we can double check that. Let's take a stop right here. So we need to figure out and write out our strain for the old stress, new stress, all those other stuff. So our old stress was as follows. So this is once we're in our original coordinate system. So my old strain is going to be simply S dot my old stress. So that's fantastic. So my new strain will simply should be just T dot old strain and then slash dot theta goes to minus 58 because that was the rotation, the clockwise to get there initially. We could also prove that in another way. So I also have my new stress. which was that tensor as well. So if I do inverse of t dot that, and then if I do s dot this, and if I do t dot this, this should give me my new strain as well, slash dot my theta goes to basically my minus 58, and voila, I get the same answer. So that's a nice double check. So I've got old coordinate system, new coordinate system. I could also again do, so if we look at my new stress, which is my new stress, sorry. So new stress, oops, actually let's do old stress. Old stress. So if we look at our old strain, so if I do slash dot, my theta goes to theta p, and we could go actually we need to do t dot, and then voila, no shear stresses. I could also go to theta p plus 45, and then same value here. I've got my values of maximum shear strain as well. Fantastic. What is the shear modulus for this material? So we know our relationship that my shear modulus, whoops, let's go over here. My shear modulus, let's go ahead and write this down if I can find my pen. So I know that tau equals g gamma. So I also know that my epsilon 1, 2 equals gamma 1, 2 over 2. And I also know that my basically my relationship that epsilon 1, 2 is equal to 1 plus nu over e times sigma 1, 2. So you can make the relationship that my g is equal to basically e over 2 times 1 plus nu. My Poisson's ratio here. So I know my Poisson's ratio and all that good stuff for my ceramic. So I can go ahead and, so I need to do, my g is just going to be equal to my y divided by 2 times 1 plus nu. And voila, there's my shear modulus. We've got it. And that's it. So for the following stress tensors, write out the angle to reach the principal and maximum shear stresses. So let's go ahead and let's find that. First off, I know that this, I'm not even going to solve this problem because it's not symmetric. Write out for the strain rotation for the 1, 2 plane. So again, I could do this fairly straightforwardly as well. So I could do my, I'm going to clear, I'm going to clear everything. So I'm going to go ahead, evaluation, quit my kernel, local, there we go. I'm going to go all the way back to my T. So there's my T matrix, there's my T matrix here. So this is my, stress, so, or strain. So strain equals 87. I'm going to keep this in, we'll write it out. 87, 24, and minus 18. And I could do that times 10 to the minus 6. So that's my strain. So I could do T, or actually I could solve T dot strain. And then I could look at the third value here. Set equal to 0 for theta. So let's look at that, solve that numerically. Oops, let's go ahead and take a peek. Oops. Let's go, where am I at? So let's go ahead and look at that value here. It is minus 18, 87, 24. So let's actually blow it up. So I'm gonna pick, let's see what this value gives us. Let's see, 75, I could do that, but I can also just do this minus, either any angle is gonna work, but I'm gonna say this is my theta p. So that's my principal. So let's go ahead and let's look at here. So found the angle, and then also look for, we could do the same thing for, take this and solve, although I think it's going to be plus 45, we'll double check, and solve the derivative of this, of 3 with respect to theta. Solve here. Let's blow this up one more time, and let's pick out a value. So let's do this. What value will this be? What do you know? if I do theta p plus 45, voila. There we go. So I've got the values also for the strain tensor for rotation of 16 degrees counterclockwise. So again, I could do t dot strain, what is it, 15 degrees? 16 degrees, slash dot theta. Theta goes to 16. Let's look at this numerically, and that would be my stress tensor. There you go. And you could double check that. So we could do the eigenvalues. Actually, we can't do it of the tensor, but again, we're treating this as plane stress, so we're not looking at the 3D state yet. All right. Falling cylindrical pressure vessel I'm working with. I measure the strain in the 2-2. So again, I'm assuming I'm thin-walled. So my strain in the 2-2 is my hoop. My strain in the 2-2 is equal to my strain in my longitudinal. My strain in the 1-1 is equal to my strain in the hoop. And I'm going to write out, I see that the stress in the 2-2 is 500 megapascals. So I'm going to start to write out some relationships. So I'm going to clear everything, quit my kernel. Got it. So now I'm going to do that so sig h equals del p times r divided by t. Sig L equals sig h divided by 2. If I'm in a thin-walled pressure vessel, we're not sure yet, but we're guessing that's the case. My EH is equal to 1 divided by y times sig h minus nu times sig L. And my EL is equal to 1 divided by y times sig L minus nu times sig h. And we have that. So my EH divided by EL, so we could actually full simplify. So we have this relationships here. So in this problem, I'm told that my EH is equal to, so my 2-2 is my EL, it's 0.44. So I have something divided by 0.0004, and this is 0.0012. So 0.0012. So this is 3. So let's say EH divided by L slash dot nu goes to 0.2. Ah, it's a ceramic material. So I know that my nu equals 0.2. I know that my Young's modulus is equal to 300 times 10 to the 9th. So I can start to solve for these values. So I'm going to solve that my stress in the 2-2 was 500 megapascals, so my sig L, so I'm going to solve these equations. Sig L equals 500 times 10 to the 6. I know that once I solve for that, so that's one equation. I know that my EH is equal to, so my hoop strain was 0.0012. I know that my EL set equal to 0.00, where is it? 0.0004. And then I need to solve for my unknowns, which is simply just going to be del P, R, and T. Oops, let's see. So let's look at sig L. So I've got this, I've got sig H, and then I also, let's say also that sig H equals sig L divided by 2 equals 250 times, actually, my sig L is that, my sig H is twice that, so it's 1000, 10 to the 6, EH is this. Let's see what we've got here. So EH is as follows. So you have del P, R, and T left to solve for. We have EL as well. So we should be able to have 1, 2, 3 equations, 3 unknowns. So we should be able to solve here. So let's see what is not being enjoyable here for our problem. So our EH in the 1-1, so our sig H is 1000. So we should be able to kind of solve here for this problem. You see, we're not able to solve it, so it is not a thin wall pressure vessel. So something strange is going on with this problem. So Last one. Let's look at the stress state below for the fully 3D stress state, and then for one that's rotated as well. So we have 1, 2, and 3. And so if we're first rotating, essentially for our RVE, so we're rotating 70 degrees counterclockwise around the one axis. So we're first, so this is going to be our new 3 prime. So this is 17 degrees, and our new 2 prime is going to be here. So 17 degrees, 17, 17. And then finally, or the next rotation, we're then going to do 97 degrees counterclockwise around the 3 axis. So we're going to do 97 degrees clockwise, so instead of counterclockwise, around the 3 axis. So it'll rotate essentially out of the board, or actually kind of around this way. So we're going to rotate, so our 1 will be essentially over here. So this will rotate again, actually, sorry. It's going to rotate clockwise, so clockwise around here. So you're going to do these rotations, and then we'll plug into Q. So we're looking at this complex stress state, and we need to find out the new, basically, rotation in this kind of new direction. So we are rotating 17 degrees counterclockwise around the one axis first. So our new 2 prime is going to be like this. Our new 3 prime is going to be like this. And then we'll do a 97 degrees clockwise rotation around the 3 axis. So to make our lives easier, we can basically look at this rotation matrix around the one direction. So I could do 1, 0, 0. So if I'm looking for my new kind of one direction, so if I do RM1 dot this slash dot theta goes to, we're 70 degrees counterclockwise. Makes sense. I'm still in the one direction. So I could do the same thing for my new values. So I could do 0, 1, 0, and I definitely get a value here. And then I could do the same thing for my 3 axis. So after this single rotation around the one axis, this is my new 1 prime, 2 prime, and 3 prime respectively. So I'm just going to take this and I'm going to also rotate it now in the next direction. So I'm going to do my RM3. So I'm going to do my RM3 dot basically 1, 0, 0, and slash dot theta goes to, now we're 97 degrees clockwise, so I'm going to do minus 97, and that will be my values here. So I'm going to do the same thing, copy this a couple more times. So 1, 2. So I'm going to take my new 2 prime, which is this. So there's my 2 prime. I got that, and then my 3 prime will be right here. So to get our 3 prime, we're just gonna, excuse me, to get our 3 prime, we're gonna take this, or plug it right into here, and then 1 prime, 2 prime, 3 prime. So we've got our vectors. So I'm gonna do 1 prime equals this, 2 prime equals this, and 3 prime equals this. So 3p. And then I'm also going to do 1 is 1, 0, 0. And then we could do 2 is equal to 1, actually 0, 1, 0. And 3 equals 0, 0, 1. So now I can start to find the angles. So I'm going to solve. So 1 dot 1p set equal to magnitude norm 1 norm p times cosine of theta times degree. Solve, and then I guess now do that for all the values. So I could say that a equals 97. So 1 and 1 prime, 2 and 2 prime, and all those values. So let's go ahead and let's work through those. In just a second, I want to pull up the definition of those matrices here. So our A is 1 and 1 prime, so B is going to be between 1 and 2 prime. So A equals B equals this. C equals 3 prime t equals 2 and 2 prime, 2 and 1 prime actually. Two P B C D E F is going to be 3 prime. G is going to be between 3 and 1 prime. F G equals this. 3 and 2P. 3 equals 3P. 17. So, got all those values. So now I could go to my Q expression. So let's go to Q. Way down here. There we go. So my Q is equal to this with all those values. So you can do that numerically. So that's my Q function. And I'm going to do transpose Q dot, let's go ahead and write out the stress tensor. So my stress equals 87 minus 18, 28, minus 18, 24, minus 16, 28, minus 16, 17. So I can do transpose Q, stress dot Q slash dot. Okay, that's it. And let's look at matrix form. And that's it. That's our stress tensor. So again, more likely you'll get something more like an eigenvalue problem with your eigenvectors. So I could, for example, if we need to find what's the principal stress state of this stress, so eigenvalues, stress. Let's look at this. And then I could also find out the eigenvectors of stress. Good. So now we're looking at the 1 prime, 2 prime, 3 prime that diagonalizes this matrix that only gives these values. So you may be asked to kind of write it out given this basis set to see if it's a principal stress state, if it's not. So that's it. Thanks and good luck on the exam.